Okay, so let's continue our discussion with the Bessel equation and the Bessel functions. So I mentioned already in the previous clip done on Maple that the Bessel equations of order n, as with any homogeneous linear equation of order 2, that is the order of the ODE is 2, has the solution in terms of linear combination of two independent functions. So let's write formally our definition first of all. So the Bessel equation, so the Bessel, we wrote that actually last time, but let's write it again. So the Bessel ODE of order n. Now I should point it out here that the order here refers to that constant that appears in the Bessel equation, because as a differential equation, it's of second order. So the order of a differential equation, that's always 2 in this case. But then the Bessel of order n refers to that constant that appears as a coefficient of y. So the standard form of the Bessel ODE of order n will be x squared y double prime plus xy prime plus x squared minus n squared times y equals 0. So n can be really any number, but in our case, as I mentioned before, we're going to limit ourselves to the case when n is a natural number, 0, 1, 2, 3, and so on. So as I showed you before, in the Maple exercise, the general solution of this ODE is a linear combination of two special functions, the so-called Bessel functions of the first kind, Jn of x, plus C2, the Bessel function of the second kind, Yn of x. So Jn of x can be shown, I'm not going to show you the proof, I'll show you actually how you can check that this is indeed one of the solutions of this ODE. So one can show that Jn of x can be written in terms of a power series with this rather complicated format. So summation from 0 to infinity of minus 1 to the k over k factorial n plus k factorial and then times x over 2 to the power n plus 2k. So this is called the Bessel function of the first kind. So I'm not going to take any time now to waste with discussing how you obtain the Bessel function of the second kind, because as I mentioned in the previous clip, we don't use it for our purposes because of the continuity assumptions of the solutions that we will impose when we solve the boundary value problem. So suffices to say at this point that Yn of x, the second component of the general solution, also known as the Bessel function of the second kind, is always discontinuous at 0. Which means, let's write this as a remark, because of physical assumptions, in solving boundary value problems, will require typically that this constant C2 equals 0. So again, to anticipate a little bit, the Bessel ODE will pop up as a Sturm-Liouville problem in solving various boundary value problems, in particular the heat equation, for example, in cylindrical coordinates. So the domain of this function will be rho in that case, or whatever is the notation for the radius. The domain will be between 0 and some number, right, depending on the radius of the cylinder. And for the solution to make sense from a physical perspective, obviously at the center of that cylinder you should have some temperature, which should be a number, but definitely not infinity or minus infinity as it happens here. So you could think of the so let me write it down here actually. So regardless C2 equals 0 because, let's finish this phrase here, because Yn of x is discontinuous at 0 and infinite, actually, minus infinity, if you remember that graph. So that can happen from a physical perspective, right? So you could think of this C2 equals 0 as coming up from one boundary condition, but the boundary condition essentially is stating that the solution should be continuous. So you'll see later that boundary conditions don't necessarily have to be in terms of there's a number, a specific number for this boundary point. It could be also a continuity assumption in itself, which will basically give you an information about some of these coefficients, which in this case means C2 equals 0. So that is the reason why we're not going to bother too much with the Bessel function of the second kind, because its coefficient in the solution will always be 0 because of these physical assumptions. And as I mentioned before, since we don't have a solution in the closed form in terms of elementary functions, one can obtain a solution in a series form, and that happens to be in this format. So the way to obtain the solution is to assume a power series format, and then you plug in that format into the ODE, and with some rather tedious work, you can come up with a formula for these coefficients. So I know this looks kind of ugly and scary maybe, but this is essentially a power series. And these coefficients happen to be the way they look like just because, well, that's life. That's how they come up to be once you impose these coefficients to satisfy the equation, the ODE. So it might be useful to write maybe one or two terms in the beginning. So for example, in this summation, the first term, when k is equal to 0, is minus 1 to the 0 over 0 factorial n plus 0 factorial x over 2 to the power n plus 2 times 0. And then if the second one will be minus 1 to the first, 1 factorial, n plus 1 factorial, x over 2 to the n plus 2 times 1, and so on. So, for example, here minus 1 to the 0, 0 factorial is 1, remember by convention, so this will be 1 over n factorial, x over 2 to the power n. The second term will be, well, will be the minus 1. 1 factorial is 1, n plus 1 factorial, x over 2 to the n plus 2, and so on. So the Bessel function of order n starts with x to the power n. If it's so, depending on the order of the Bessel equation. So on the next page, I'm going to actually show you how you check that this is indeed the solution of the Bessel equation. It's going to be a rather tedious process, but the reason I want to show it to you, it's not because we're going to use it in the class too much. You will have a similar homework question. It's just a bit easier than the case I'll show you in the lecture. But I want to go over this process to give you as strong as possible a motivation why, if we deal with Bessel functions, we really need to use some computation rules so that we don't really have to replace the Bessel function all the time with the power series, because the process will be very, very tedious if we don't come up with some computation rules. So before we move on to showing this, checking essentially that Jn of x is the solution of the Bessel equation of order n, let me just state a couple of things which will be useful for the mechanics of doing this in the next part. When you have a power series, let's say you have the summation from 0 to infinity x to the power k. It is often necessary to change the first value of the index. So in this case, if you expand the summation, this is x to the 0, which is 1 plus x squared, and so on. But often, if you want to combine this with a similar series that goes to the same powers, but with a starting index that is different than this one, you should be able to change the first index of k and still have the same power series in this equality. So in other words, let's say I want to write the same summation, but with the starting value of k equal to 1. Whenever you advance the starting value of the index with 1 unit, you can achieve the same powers if you decrease the power of x by the same unit. So notice if I write, instead of summation from 0 to infinity x to the k, summation from 1 to infinity x to the k minus 1, this basically gives me the same series. Because now you have x to the 1 minus 1, which is again 1, x to the 2 minus 1, which is going to be x to the first, x squared, and so on. And you could do this trick whenever you want to. I mean, for any number. Let's say I want to start from 2 and I want to have the same summation. All I have to do is to subtract 2 from k everywhere in the series, and that will give me, again, the same series. So all I just changed the starting value of the index of the power k. So the reason I'm showing you this is because if you want, as you will need when you check this series to see if it's a solution of the Bessel equation, whenever you need to combine various summations together, you should have essentially the same starting value of the index, so that the value of k, when you combine the inside of the series, is the same. And also, obviously, the power of x should be the same when you combine them. So with that in mind, let's move on with the next part, when we're going to deal with checking that the Bessel function of the first kind indeed solves the Bessel equation of order n. So stay tuned.